Hello, hello. Um, if you can hear me, put something in the chat to let me know that it sounds okay. Just say something, anything, and just say hello. Okay, so I can see who's here. So just type in the chat and then we'll get on our way. I just want to make sure that you can hear me. Something, excellent. Ugh. All right, so we're going to look at assignment 2. Which is due in nearly a week's time. Um, and we're just going to go through it step by step, having a look at how to implement it and clarify anything that needs clarifying. So let's start from the start. So I've got the assignment here. The assignment is one C file. Okay, so this is not multiple files. And you're going to use LMS to submit it. Okay, it needs to run on the Unix server through PuTTY. Okay, so make sure that it does run on your own machines. All right, so what we're going to be doing in this assignment is calculating the voltage, current, and impedance for a bunch of electronic components. This includes resistors, capacitors, and inductors, and how they're connected will change this voltage, impedance, and current, as well as their values and also the original voltage. So we've got a bunch of formulas here. We'll come back to that. We don't need to worry about that too much. We've got two configurations, parallel and series. We can come back to that as well when we get to those. All right. Function prototypes and includes. So you need to include the standard io.h library and the standard lib library. You can't use any other libraries for this assignment. Okay. You need to use these function prototypes. You cannot edit these. You can change the names if they're a bit too long for you, but it still needs to be the same thing. Okay, so you can't add extra parameters or remove parameters. Okay, and 4 of them you should have already done from lab 5. So you've got 2 other ones, which is calculate impedance, and then you've got print results. And we'll look at these in detail when we get to those. All right, first things first, we're going to have our main function. Okay, so we have our prototypes, which are going to be above main, and then we're going to have our main function. The first thing we're going to do is we're going to print to the screen our student number, our name, and the assignment number. Quite a few people had difficulty with this. It's just printf, what we've been doing since the start. So just printf with this in brackets. All right. The next part is asking the user for information. So the program asks the user which circuit they'd like to evaluate, the frequency in hertz, the source voltage, and the number of components, and stores the results appropriately. Now, with this, you've got to have a think about the data. So we can have a look at these inputs. We have, do you want to create 1 parallel or 2 series? And because it's only a 1 or 2, we can assume the type has to be integer. When we look at the frequency, when we look at the frequency, we can also assume that it's an integer for this problem. The source voltage has to be a double, okay, given the information that we find out later. And then the number of components has to be an integer. We can't have half a component. Okay. Now, for the source voltage, whilst it will be a double, what will be entered will always be an integer. So It's up to you if you want to store it as a double or if you want to store it as an integer. Either will be fine. You can always assume that the user will enter something valid here, okay? Except for the incorrect type of circuit. So they might enter a different integer value, such as 3 or 0, okay? And you just need to print a message. This is very similar to what we did in assignment 1. So printf, scanf, printf, scanf, printf, scanf, and then just checking this. As I said, for these, you can assume that they are right. It's just this very first one that you can't. So now what we're going to do is this part here. Now, if you use a two-dimensional array, you will get 0 for the assignment. There is a reason for this, but I'm not going to get into why. Okay, so we need 6 pointers. And I might make the pen a little bit smaller. It's a bit hard to use. Let's go 5. 4 is good enough. All right, so we need 6 pointers. Okay, you create 6 different pointers. Okay, currently with pointing to nothing. Okay, so 1, 2, 3, 4, 5, and 6. Now, the impedance, the current, and the voltage here all have a real and an imaginary part. So to make my diagram easy to read, I'm just going to write IR for impedance real. I might actually put it up under each other. I'll put I imaginary for impedance imaginary. I'll put CR for current real, and I'll put CI for current imaginary, and I'll put VR for voltage real and VI for voltage imaginary. Okay, so I've got all of these pointers. Now, why it's important that these are pointers is that we know that there's not going to be one impedance. There's going to be impedance for every single component in the system plus the total. So if I have 3 components, then I'm going to have 4 sets of impedances. I'm going to have 4 sets of current, and I'm going to have 4 sets of voltage. Okay? Now, because of that, I need to dynamically allocate memory for each of the pointers as size of double times number of components plus 1. This bracketing is kind of important, and we'll talk about that in a second. So we're going to use Malloc, okay? And we want to return a pointer from Malloc such that we can store the pointer in one of these. Okay, so let's do one of them. Okay, so we need to use Malloc. Okay, and we need the impedance real, okay, to be size of double because we need doubles. Okay, size of double. And we need the number of components plus 1. And the reason we need plus 1 is because we also want to store the total. And we can have a look at this on this table here. So if we had 4 components, we'd have 1, 2, 3, 4 plus the total. So that means in total there should be 5 doubles. Now, why is it important that this is in brackets? Okay. So if a double is 8 bytes, okay, and I need 2 of them, and I have 2 components, let's say, then I actually need 3 because I need 1 for the total. So I have 8 times 3. Now, if you do not put this in brackets, oops, plus, okay? If I do not have this in brackets, it's not going to create 3 doubles. It's going to create 2 plus a tiny bit, okay? So the brackets here are very, very important, and if you forget them, that may cause you problems, okay? Because we want to have 1 for each component plus a total, okay? So we know that this is creating doubles, okay? So in memory, we should get some doubles, and we're creating n plus 1 of them, so n being the number of components. So this should create me n plus 1 components. Now I'm going to give a value to n to make it easy, and I'm just going to say n is 2 so that I don't have to draw too much. Okay, it could be any value, okay, depending on what the user put here. Okay, but I'm going to give it as n is 2. So where does this get stored? Well, it gets stored here. So you could just put the assignment here. Because we have doubles, the pointer has to be a double star, okay? Because a pointer to a double needs to be a double star. And so we could put our malloc here, or we could put it on the line below, okay? So you can do this all in one line if you like, or you can use this again down on another line. So what would this look like? So I need to change that. Sorry, the razor's not very good. That's better. All right. So get rid of that. Get rid of that. Okay. So why am I still on the razor? All right. So our n is 2 plus 1, we get 3. Okay. So we create 3 doubles when we call this first malloc. Now we have to do this 6 times, one for every single one of these. So the first time I call it, I create 3 doubles. Okay. And these are all double star, double star, double star, star. And so these are allowed to point to this array. Now that first memory address from our malloc is going to be stored here. Okay. And so that means that this pointer will point right here. Okay. And then we'll do a malloc for the next one. Okay, you can typecast it if you like. And so what we should get is pretty much the same thing for every single one of these. Oops. Why didn't that work? There we go. Alright, we're starting to build up quite a bit of memory. Depending on how many components there are, this can get rather big. So now we just join them up, okay? So every time we call a malloc, it's going to create 3 doubles because I've got 2 plus 1 here. Remember, this is given by the user beforehand, okay? So it's not always 2, this is just a value I've chosen. Alright, so I'll do this one first. I might put them in different colors to make it clear. We've got the current. It's going to be here. Current imaginary, which is going to be here. Let's go a different color again. So we've got the voltage real, which can be down here. And we've got the voltage imaginary, which is going to be down here. Now I haven't given any of these values yet, okay? But you can see by using malloc that I basically create this table. Okay, so if the user entered 3, these should all be 4 long. If the user entered 5, these should all be 6 long. Okay, and by using malloc with size of double times the number of components plus 1, where this is in brackets, you should get this. You do need to call malloc 6 times here. Now, the user enters the voltage. Okay, so this here gives us the total voltage. Okay, so keep in mind that all of these last ones are the total ones. Okay, so because the user gave it to us, we know that the source voltage is 12. Now, when we have 12, but we don't have any imaginary part, we could just write it like this, okay? Because 0 times the imaginary number is 0. So basically, whenever we just got a real part, we can rewrite it as this, and so it means the imaginary part is 0. Okay. Now, if we have a look here, this is what we're doing. Okay. So remember n, or number of components, for our problem is 2. So if I go to voltage real 2, okay, and here I'm using array notation. So I go to voltage real, okay, and I'm using array notation, so I'm actually going to the element. This is element 0, this is element 1, and this is element 2, okay, because n for our user is 2. Okay, and I'm just going to put the source voltage that the user entered. So for us, let's say the source voltage the user entered is 24. Okay, so we go down here and we get 24. We also have the imaginary part. So this is also 2 because for our user, we've got 2. And we just put a 0 straight in there because we know that the imaginary part is 0. And the user will always make that 0 for our problem. Okay? The user can't enter the imaginary part for our problem. All right. So we've done that. And we've built this table. Okay? So we've got the impedance of component 1, the real part. So we've got all our impedance reals. We follow this. And this one here should be the impedance real part for component 1. Okay, and this could be 100 long or 10 long or however long, depending upon what the user put in. And it is still only 1 malloc per table. All right. So once we've done that, we also need to store some more information. So we haven't filled any of this out yet, which is fine. That comes later. But we also need to know what the components are. So I know that there's 2 components for our system. Okay. But I don't know what they are, and I don't know what value they have. Oh, okay. So someone asked why it's 0L. Basically that's 0 long. Basically you can end up with a small error if you just put 0, because 0 won't be stored perfectly. Okay, because it's taken as an int and you're storing it into a double, and when it converts it, you may end up with a very, very small number, like 0.00001. It's just because you're going from one type to another, and so we specify the literal as small as we possibly can, so that it can be stored straight away. And that's why we have the 0L there. Try it without it. The program works, but you'll have a really tiny difference. And so when you go to the output, you'll notice instead of 0, you get like 1 times 10 to the negative 99 or something like that. So this is why we do this. All right. So now we're going to go and actually make the memory to store both the type of component. Remember earlier we said we've got 3 types of components. We've got resistors, we've got inductors, and we've got capacitors. Okay. So we're going to make another array, and it also needs to be dynamically allocated because I don't know how many of these components I have. So what we're going to do is going to create another pointer. Okay. And this pointer is going to be called, what's this one? It's called components. So I'm just going to call it C for my diagram. Now, it's going to store ints. So the type has to be int star. Okay. And the array is the length of number of components. So if I want number of components, I can use my n. So for my problem here, I would have 2. Okay. So my malloc is going to be my size of what I want, which is ints. Oops, that's not a very good int. Times how many I want, which is number of components. There's no +1 here because I don't need any more. Okay, this is for the total when calculating, but in terms of the components, there is no total component. So I call malloc and store that in my pointer that I just created called components, which I created as an int star. Okay, I've got an int star components, and I just create that bit of memory, and that'll give me a pointer to the start of this memory, and they're all ints. I'll do the same with this second one, which is the values. Okay. And then I get another 2 here. Probably should have done 3. It'll be better for the math, but that's okay. We'll come back to that. We can do a 3 after. All right. So now that we've done that, we've got pretty much all the memory we need for the program. So this is all our dynamic memory that we need. So keep an idea of this. You should be able to draw the box and pointer diagrams for this. I may actually just thinking. Actually, I won't. I'll do another problem after this. Okay, so now we want to actually start filling these in. Okay, so we want to get the components off the user, and we want to get the values off the user. Okay, so for each component, okay, so we're going to use a for loop. Okay, so for something, something, something. We want to go around n times, so I'm going to have an n here. It's the standard template because we're just going to increment one at a time. So you should know what goes here, what goes here, and what goes here. All right. The program asks the user for the type of the component and the value of that component and stores the types and values. When asking for the size, correct units must be shown, ohms, farads, henries. You can always assume that the user enters valid values. Okay, so you don't need to do any validation here. Okay, so you've got this text up here. Okay, enter the component type for each component where 1 is resistor, 2 is capacitor, and 3 is inductor. You'll notice that that part there isn't looping, where this part here is looping. Okay, it's the same thing over and over again. The text is slightly different because we've got if statements inside the loop, but you can see that if this was 4, we'd see another one like this. So you can see this part here is the loop. Okay, and then we've just got some text at the top. So we'll just put a printf and just put this text here. Now, there's multiple ways to go about this. Okay, I'm going to put the I there. Okay, we're using I. Now, there's multiple ways to go about this. We could either use pointer arithmetic, or we could just use array notation. It's up to you, and it's not forced in this one. So I'm going to show you both. We'll start with array notation, and then we might come back and use pointers instead, and use pointer arithmetic. So we're now going to print something to the user, which is component 1. So we'll print the word component. We want to print this 1, so we'll put a %d. Okay. Now, remember that I starts at 1, so this goes back to the lab, and we just need to print I plus 1 here. Now, we scan the user's input. Okay, you know how to do that. However, we want to actually store this number somewhere. So you've got a couple of ways to do this. So where do I want to store this number? I want to store it here, okay, because I'm looking at the first component. Now, if I want to store something here, what do I have to give to scanf? I have to give its address, okay? So scanf, if I give this address right here, it will store it right here. So what I'm going to do is I'm going to use scanf. Now, what are we looking for? %d. Now, C is a pointer to contiguous memory. Okay, so we've got memory that's in a row. Now, if we remember from the labs and the lectures, if we've got memory that's in a row, we can just use the square braces. So I could say components, where mine's just called C, okay, and I could just say I. Okay, and that would refer to this first part, but I also need the address, so I could just say CI. Now, if you wanted to, we could do pointer arithmetic here, and we might come back and actually do that, but we can use array notation, and it's usually easier for most students to get their head around, so feel free to use array notation here. Okay, remember we've got contiguous memory, so it's pointing at the first element, so this is index 0, and this is index 1. So I scan that, and a value goes in there. Let's say a 1. Okay, I get a resistor. Now, I can read this memory as well. So if I need to check whether I need ohms, farads, or henries, I can say if CI, because remember, at this stage, I is 0. Okay, it's going around the loop, equals 1. Then maybe I print enter the size of components in ohms. And I'm going to run out of room in a second. I'm really going to run out of room. Give me a second. I'm just going to make this page bigger. Canvas size. No, not that big. So I've just made the canvas a little bigger, just so that we can continue. All right. So, oops. So we're in a for loop. We've printed component 1, okay, because remember I is 0 at the moment. We're in the first iteration. The user's entered a value and we've stored it at this location, and that's happened successfully. Now I need to check if it's a 1, 2, or 3 to know if I need to print ohms, farads, or henries. Okay. And I can just grab that value back using array notation. Okay. Why aren't I writing? What is going on? What is going on? Sorry, for some reason. Oh, selected. Okay, cool. All right, so we've got if this is equal to 1, printf blah 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 ohms, else if blah 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 farads, else. Now I can say else here because we're guaranteed that the user is going to enter 1, 2, or 3. Okay, I'm not going to put the detail there. That's for you to do. I'm just going to get rid of that. I can't because it's on a different layer. Damn thing. There we go. Okay. So we've done all that. Now we need to get the size of the component. Okay. So we've printed that. And now we just need to scan in the size. I think I made a mistake. Oh, it's doubles. Yeah. Sorry. Oops. What is going on there? They should be doubles. Should have just written D. Okay, so now we're going to get the values, okay, from the user. So once again, I can use scanf, okay, and I want to store the result here, so I need the address of here. And you'll notice that that looks exactly the same as that, so I think you can work out how to do that. Okay, it's pretty much the same format, except for this time we're getting a double, okay, and it's not C or components, it's values. Okay, you can do that. All right. Where are we up to? Okay, so we've got the values. Cool. And I think that's really it for that loop. And then we go back up and do the second component. So component 2, 1 plus 1 is 2. We scan C1 now. Remember this is index 1. Okay. The pointer to contiguous memory, so I'm allowed to use array notation. I pass the address in because this is where I want you to store, or where I want scanf to restore the result. Okay, remember scanf wants a location, doesn't want a value. The user enters something, let's say they enter 2, okay, and then it'll print out, give me farads, and then I scan in the value. So that'll go here. Well, let's say 7.2 and 1.2. Okay. So we've got all those values. Aleph. All right. There's no difference. There's no, so if you use pointer arithmetic or you use array notation, there's no real difference. There there might be some differences in terms of efficiency and some maths you can do, but in this problem, really it doesn't matter. You can use whatever you like. It's not going to make a difference. If you use pointer arithmetic, you just need to be a little bit more careful that you don't write somewhere that you shouldn't, and that you don't change your original pointer. So I recommend doing array notation first, get it working, and if you want to try doing it with pointer arithmetic, come back to it. Okay. All right. We're then going to make a function call. Okay. So calling the calculate impedance function. Now, a lot of students seem to get confused by this fact that we're calling a function. We've been doing it since week 1. We've been calling printf. Okay, so we can call a function quite easily. So I don't even need to know what the function's doing yet. You should write it first, but we're not going to write it yet. We're just going to have a look at its definition. And we've got void, calculate impedance. We've got the real part. We've got the imaginary part of the impedance. We've got our components. We've got our values. We've got our n. We've got our frequency. And we've got our choice. Now, I would like to grab that. So what I'm going to do, give me a second. Where did I put that? Oh, there it is. Where is that? Oh, there it is. Let's make it a little bigger. Put that there. One. Okay. All right. So I've just copied that off the page, and I'm going to put my signature of my function here. Okay, I've just put it over 2 lines so we can see it. Okay. So I need to call this. Okay. So when I see this, okay, when I call this, okay, let's say this is my code. Now, with the void function, we should never ever see something like int x is calculate impedance. Because it doesn't return anything, it shouldn't be part of an assignment. Okay? Okay, that's a great question. Why do we need to dynamically allocate memory for the components values in an array when we have the number of components? Um, because we want to basically, we don't know the value beforehand, okay? And so we should be declaring the memory on the heap. Um, yes, you can put n there. It's not as efficient, and we don't want to do that. There's multiple reasons. We can get into it later. But basically, we don't know the size, okay? And especially for ANSI C, we shouldn't be just putting n inside of the brackets. It should always be a constant, because you're basically saying that it's static memory, and your compiler doesn't know, and so it just has to kind of guess. So if you do not know how large the array is beforehand, you need to dynamically allocate that memory. If you're using a later version of C, you can kind of get away with this, but it's still not as good. But we'll get into that a little later. I can refer you to a video I did last year. Okay. Basically, in this subject, there should be no variables inside of those square brackets when you declare something. Okay. Because n is unknown. All right. Is choice last parameter we're using for series and parallel circuit? Yeah. That's a good point. Yes, choice is basically if they chose parallel series. Anyways, let's keep going. What was I doing? Calculate impedance. So because it's a void function, when we call it, it should not have any assignment. So we're going to call this a calculate impedance function. The first argument to this function is the real part. We'll note that it accepts an address. Okay. And so what we want to give it is this here. Okay. We don't want the address of this. Okay. We want the address of the array because having this isn't very useful. Having this is very useful because this is where we're going to store our impedance. Okay. So we don't want to pointer to this because we'd need a double star. What we want instead is the value inside of this. Okay. Which is suitable because this is a double star. Okay. And this is a double star. So mine's called IR, impedance real. Okay, yours will be the full name. Same with the next one. I've got impedance imaginary. There's no ampersand. There's no stars because result table impedance real is, as we've seen, a double star. Double star, double star. They're the same type. Okay, we're passing this value. Okay, so this starting memory address of this array. We're then passing this components. So I can just pass my C. Okay. This square braces is basically the same thing as saying int star components. They're exactly the same thing. You don't have to worry about that. Same with values. I can just pass V in. N I can pass in straight away. Frequency I can pass in straight away. And choice, yes, it's basically if they chose parallel or series. Okay. So we'll look at that a little later. Okay. So we're able to calculate the impedance. We come back and our impedance should be calculated. We're now going to calculate the total current values for both the real and imaginary part and store appropriately. So let's have a look at this. Okay. So once we've calculated the impedance, okay, I'm just going to make this up. These will all be filled. Okay. Okay. So these will all be filled. The ones down here won't be yet. Okay. And what we want to calculate is this here. Okay, we want to calculate the total current. Now we've got enough information to do that. Okay, because we know this law here, which says I equals V over Z. I is our current. Okay. And we've got our V. Okay. And we've got our Z total as well. So let's do the calculation. Let's have a look at it. So I've got V over Z, so I know I need my complex division. The top of the division is going to be my voltage. Okay. Now, I don't want the whole array. All I want is the real part and the imaginary part for this last element. Now, if I remember earlier, okay, this is at n. Okay. So if we go down and I call V real n and I call the imaginary n, then that's going to be the numerator of my division. And I'm going to run out of room in a second. And that's on a different layer. I don't know which layer. Cool. Let me just get rid of that. All right. So I probably got rid of everything. Yeah, I did. Let me move this down a bit. Okay. So we now need our Z. So our Z total is going to be in the same location. Okay, we go over here, and everything moved. That was my fault. Think that through. Okay. Our z total is going to be over here, so it's also at that n position. Okay. We're going to come back down. I'm just going to move this down a little bit more room. Sorry. All right, so what do we want? We want z, which I think I called I. Yeah, I did. Cool. So we want I real, which is impedance. It's not current. Okay. And we want impedance imaginary. Okay. And what we want to do with these, so we've got our numerator, which is our v. We've got our denominator, which is our z. Okay. Now it doesn't matter if we don't know how to solve complex division ourselves. The function does it all for us. As long as we put in the real and imaginary for v and the real imaginary for z, it will work out. However, with our complex division, we remember from the lab that the last two parameters are the address where we want to store the result. So if we go and have a look, we want the address of here and we want the address of here. So we want this location and this location here. Now, I've got my current real and my current imaginary. Once again, they're pointers to contiguous memory. So all I need to specify is that n index and just put the address operator in front of it. So we've got address of current real, and the address of current imaginary n. Okay, so we should have, after we've done that, we should have two values here. Let's say 8 and 4. I'm just making this up. Okay, I'm not going to calculate it. We'll look at calculations later. Okay, so we only have a little bit left to do now. We have these and these. So we have all the currents of each component and all the currents, voltages of each component. So let's continue. So this part here, calculate the voltages and currents of all components. Now, this depends on if it's series or parallel. So you do need to check if it's series or parallel. Okay, and there'll be two sets of equations. Now, if you can't do this part, you can leave this part blank. Okay, because you'll still just have garbage values here, and the print should still work. To solve this, basically, where are we? Where is it? Where is it? There we go. Basically, you use this information. Okay, so if series, the current is all the same. If parallel, the voltage is all the same. So I'm not going to show you the steps for this because I want you to solve this one, but let's have a look at this. So let's say, what are we doing? Let's say we'll do parallel. Okay, so let's say our circuit is parallel for this example. Okay, so let's say it's parallel. Okay, so all the voltages are the same. So that just means that, where's our voltages? That's going to be 24, that's going to be 24, that's going to be 0, that's going to be 0. Okay, that's Basically, you're just copying these two values into the whole thing if it's parallel. Okay, you should all be able to do that. It's just a for loop and storing these values. If it was series, the current is all the same. Okay, so if it was series, and if that's the case, then this is going to be an 8, this is going to be an 8, this is going to be a 4, and this is going to be a 4. So you should be able to copy those. Now, to solve the other part, okay, if we need V, and I think I gave you every combination so that you can, yep. So if we need V, we can go I times Z. If we need I, so current, now just keep in mind I stands for current, okay? If we need current, I can go Z at V divided by Z. So we need voltage because we're dealing with series circuit. So for this first component, I'm just going to have I times Z. And we've got the I, okay, which is this one here. And we've got, oh, sorry, we've got the Z and we've got the I here. Okay, so we can times them two, and that'll give that. We can then, need another color. It's getting really messy. We can then do these two, I times Z, okay, and so on. So this part's left to you, okay, and if you can't solve it, it's fine. You can still print out what you get, or just set them all to 0. You should at least be able to get this part. This last part is a little bit harder, but that part's left for you. All right. All right. All right. So that's that part. Now I can't give you too much information about this, okay? Because this is your demonstration of your problem solving skills. And then we call the print result function. And we'll also talk about this in the program appropriately, and then we'll look at the calculate impedance and the print in detail. So the print result one, you can see this here. This call is very similar to the call we did before. We're just passing everything in this time because we want to print everything. So passing in the impedance of the real part, impedance of the imaginary part, the current of the real part, the current of the imaginary part, the voltage of the real part, the voltage of the imaginary part in, and then components. Okay, so that should be fairly easy. Okay, just keep in mind that this int brackets is the same thing as int star. Okay. All right. Where are we? Where are we? All right. End the program appropriately. So this is kind of important. You've got dynamic memory, so you need to free it. Okay. So if I go and have a look here, okay, I can see 1, 2, 3, 4, 5, 6, 7, 8 pointers pointing to dynamic memory. So it means that I need 8 frees. Doesn't matter how long these are, okay? It's always going to be 8 in this case. Okay. So that's that first part. And I have no clue where I put the other part. Oh, there we go. All right. Cool, cool, cool. All right, so now we're going to do this. I'm just going to refill my drink, and I'll be right back in about 2 minutes. Uh, Okay. Um, Someone just had something about a error. Um, Expected semicolon, comma, or bracket before ampersand. Um, I would personally just have a look before your ampersand or multiple ampersands in your complex division and make sure there is a comma there. That's probably what the problem is. That's missing. All right. So now we're going to calculate the impedance for both the real and imaginary. So I'm just going to get some values that I've already pre-calculated. So grab is sorry, just grabbing something. Over annoying. Um, Alright, just give me a second. I just need to grab something. Okay, sorry about that. Okay, I've got a weird error message. Before I add a double in front, if you're calling a function, you should never have the type in front of it. Are you calling or are you creating the function? Because it's two different things. Okay? When we call printf, for example, okay, if I call printf, I would never write const car star hello world. Okay? And that's what you're trying to do by adding the type in front. There should never ever be a type in front of your argument. Okay? So when you're calling a function, you shouldn't have double or double star or any of that inside the call. Okay? I see here, if I did double star IR, that's wrong. Okay? It should be in the definition, but not in the call. Okay? Printf, scanf, we don't write the type beforehand. I don't run const car, I don't write double, etc. It doesn't make sense. So I never write scanf for example, that's a double star. So I don't write double star ampersand CI. So you shouldn't have double anywhere in your call. You should have it in your definition, but not your call. All right, let's continue. Where am I? All right. So what we're going to do now, and I may need, still can't find it. Oh, that's works. No, that's okay. All right. So I just need to open up. You're gonna have to print the show me the line. Um, it's something in there you're missing. All right. So we need to put together some values for this. So I'm going to put together some memory. So we're going to have 3 components. Okay. And we're going to have a resistor, a capacitor, and a inductor. Okay. Now, this is after we've called the function. So we should, inside the function, where am I? We should have, I probably should copy that across. Copy that across, make it easier. Sorry. Okay. So once I've reached the function, I'm going to create all of these variables. And we're assuming don't just get rid of square brackets. Put what is correct. Okay. In your call, for example, if you were missing these square brackets, and then you would get a warning, and you're also passing a memory address rather than a value. So don't just remove things until it works. Okay. That's probably the one worst way to program. Okay, because as we showed in the last lab, you can have something that has no errors and it still will crash. Okay, so don't just remove stuff until it works. All right, so we've got our components. Okay, we passed the pointer in as we showed before. So, oh my god. Yeah, I don't care. Cool. All right, so we've got our components. Okay, and that's an int star. Okay, because we've got the square brackets there, it's the exact same thing as saying int star. You can change that if you like. You can have int star components or you can have square brackets. It is exactly the same thing, so either should work. Okay, and these are all ints. Okay, remembering that the calling function passed in this memory address as we showed before. We have our values. We need those as well. This is V, and this is a double star, and this will also point to some values. The values we're going to go with are we Yep. We're going with 40 ohms. We're going, need more room. We're going, let's make this a bit bigger. Oh wait. 40 ohms for our resistor. We're going 0.0003 farads for our capacitor and 0.2 henries for our inductor. And we need the pointer to the start of that. These are all doubles. Okay, so we've done that one. We've got N, which is going to be 3. Okay, we got our frequency, which is going to be 60 hertz. So F 60. We've got our choice, which is going to be parallel. Okay, so choice, maybe parallel, which I think is 2. And then all we need is, so we've got all that. Then we just need our impedance real and our impedance imaginary. Okay, which we've passed the addresses in from what we did before. Okay. And that gives us everything that we need. So we've got our impedance real and our impedance imaginary. And these are all blank as we saw before. Okay, they're blank until we finish this function. Okay, so I can get rid of that. So we've got everything we need. Okay, and these are all double star. And this is double, 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 double. Okay, so this is everything we have access to whilst we're in this calculate impedance function. So let's have a look. We need to work out basically the impedance of each component first. Okay, so this is the first part of this function. So calculate the impedance for both the real and imaginary parts for each component using a for loop. Now the reason we need a for loop is because we need to go through each component. Oh, and this also has a total. Sorry. Okay, so this is going to be component 1, this is going to be component 2, this is going to be component 3, and this is going to be the total. Okay, so we've got the impedance of the real one and the impedance of the imaginary for the first component. So let's have a look at this. So we need to use a for loop, as mentioned. So for, we can just use I again. Okay, and we've got N. Okay, so we're going to go around this 3 times. Okay, you can fill in the blanks there. We need to check if the component's a resistor. So we can do that using our components. Okay, so I can say if Ci is a 1. Okay, remember 1 being a resistor. Remember C is components. I've just called it C. In yours, it'll be called components. But remember, it's contiguous memory, so I can use the square braces there rather than pointer arithmetic. Okay, so this is just saying C0 is equal to 1, else if Ci, okay, is equal to 2, else blah blah blah. Alright, so we have a look at this information here. Okay, if the component is a resistor, the impedance real is the size of the component and the impedance imaginary is 0. Okay, and if we go back to our background information, okay, the impedance basically just equals the real part. So we don't have an imaginary part at all. So we can just say that basically this should be 40 and this should be 0. So how do we do that? Well, if it's a resistor, then the imaginary part is going to be 0, and the real part, okay, is just going to equal the value. Okay, so let's have a look at that. So we've got the value here, okay, which is 40. Okay, so let's say I is 0 at the moment. So we come in, is components 0, 1. So we go to components, we go to index 0, and we get a 1. Yes, it is. Cool, so it's a resistor. We go and grab value 0, which is 40, and we store that in the real part. Okay, so we've got the real part, index 0, and we're just storing that. And then we store the imaginary part as 0. Okay, so for resistors, the imaginary part's always 0, so we can just write that it's always 0. Now, if it was a capacitor instead, okay, then the real part is 0. So I think you can work that out. But we've got this negative XC here. So we have to go to our documents here, and we see that we've got this formula, okay, and we've got 1 over 2 pi times F times C. Well, we've got all that information, okay. So basically we can say imaginary part for I is going to be negative 1 over 2 times, now you can declare pi somewhere, or you can use, actually you don't have access to math library, so you need to declare pi somewhere. I'll let you do that. And then we've got F. So we have F, so we can just use it. Okay. Times the value. Okay, so if we have a look at the formula, we've got the C. Okay, and we've got C, okay, which is this value here. Okay, so we can just go value I. Okay, and that means that when we do this, we go for our second one. Okay, so now I is 1. Okay, we go is component at index 1 a 1? No, it's not, it's a 2. Else if is component at index 1 a 2? Yes, it is. We set the real part to 0, and we set the imaginary part to this value here. Okay, so we calculate that all out. And what we should get from that is negative 8.842. Okay, and this is the same example as the worked example. Okay, and then we do the inductor, and you can do that part. Okay, you've got the formulas, you can work that out, and we should get 75.4. Okay, and if you want, do a quick check afterwards and just make sure that you do get the right values. Okay, so now we've done all that. Now we need to do this. And this is the impedance of the total. So there's lots of ways you can actually do this. Okay, and it's up to you how you do this. Okay, so we'll go through the way suggested, but there are better ways to do this. All right, so give me a second. All right, so we're going to create temporary variables to store the sum. So we'll just create some variables. We'll call it, I don't know, sum real maybe, and we're going to set that to 0, and we'll create another one which is sum imaginary, which is 0 as well. Okay. We're then going to, so we've got the sum for the real part, and then we're going to create two variables for the total impedance. Okay. So we'll do that as well. We'll create another set, which is, I'm just going to call it tot real, tot mag. You can do a bit better name than that. No, I'll leave them uninitialized. You could just set them to 0 to make you a little bit happier. And then we're going to look at if they are in series or if they're in parallel. So what did I say? I said in parallel. So we're going to do parallel for the example. So if it's in series, okay, you should know how to check that by now, then we're going to iteratively add up all the real parts, and we're going to iteratively add up all the imaginary parts to give the total. Okay, so let's have a look at this. So if it was series, okay, all we would do is go 40 plus 0 plus 0, and we go 0 plus negative 8.842 plus 75.4. And we've seen this in the labs before, that we start off at 0, and then we add the 40 to it, and then we add the 0 to it, and then we add the 0 to it, and we start off with 0, and then we add the 0 to it, and then we add the negative 8.842 to it, and then we add the 75.4. But we don't need this. We can do both at the same time using our addition function. Okay, so we've got our, what's it called, complex addition. Okay. So we can send in the sum, okay, and we can send in the next thing we'd like to add. Okay, so the first two are going to be the sum. This is going to be the thing that we want to add, and this, what we get back, I should draw these the other way, okay, is also going to be the sum. Okay, so for example, for the first loop, we're going to have 40 and 0 coming in. We've got 40 as the real part and 0 coming in. Our sum is currently 0. Okay, and then when we've done the function, we should have 40 and 0 here. Okay, then on the next loop, we're going to have 40 and 0 coming in. We're going to have negative 8.842 and 0 coming in. And the sum coming out should be negative 8.842. So let's have a look at how we do this. All right, so we know that we need a for loop, okay, because we're going through every value to get the total, okay. We're going from this one to this one to this one, and then we'll get to the total eventually. So we'll create an I variable somewhere. You can do that. And what we're going to do is just call our complex addition function. Okay. As I said, the first two things that we want to pass in is just going to be our sum real and our sum imaginary. Now these are not pointers, So we don't have to dereference them. We don't have to send the address in. We don't have to do anything weird with them. Okay. The next thing is that we want these values for the first loop. Let me grab a green. Green's always good. We're going to grab these values for the first loop. Then we want to grab these for the next loop. We need these for the next loop. So we know we need I somewhere. So we're going to need, what did I call it? IR. IR I. And we need I. Okay. Because I want to pass in this one. Then I want to pass in this one. Then I want to pass in this one. And then on the output, what I'm going to do is I'm going to pass in the address of some real. Because I want the result to be stored where some real is. And so that means when I come back next time, when I pass in the next sum real, it'll be a new value. Now this is perfectly fine because remember, when we call this function, it passes a copy here. Okay, and it passes a copy here. So even if I change some real while I'm calculating, it's not going to affect the one that came in. Okay, because the one that came in is just a copy. And so I can pass this address in as well. Okay, and that's basically how I would do the series part. And as I said, there is other ways to do this. We also need the total impedance. So we can just put the total real and we can just grab the sum. Now you could have just used this the whole way through as well. Okay. So alternatively, we could have parallel. Okay, and we need to deal with that. So this one here is a little bit harder. Okay, so create a set of temporary variables for the result of the division. Okay, so we need another set of variables. So I don't know, temp div real and temp div imaginary. And what I'm going to do with these is I'm going to use these for the division. And why do I need to do this? Okay, so let's go back and have a look at this calculation here. Where are we? Yep. All right. So did I draw this out nicer? Ah, I didn't put it on the sheet. So we're going to be doing this formula here. Okay. So basically, when you have a couple of components in parallel, okay, we have this plus this plus this. Now this is the same thing as saying this plus this plus this. Okay. And what we want to do is pretty much the same thing as we're doing with the addition with this part. So we want to add up the sum. But in between, we also need to do a division. Okay, so it's going to be a two-step process. So we're going to calculate the division, and then we're going to add it to the sum. Then we calculate the division, and then we add it to the sum. Then we calculate the division, and then we add it to the sum. So because we're doing this calculation of the division, we need somewhere temporarily to store that result before we add it to the sum. So what we're going to do here is we're going to iterate. Once again, you know what iterate means. Okay, so we're going to have a for loop. We now are going to divide the component's impedance value and store the results appropriately. So we know that we're going to need complex division. Okay. And we know that the thing that's getting divided, we go back, okay, is one real, 0 imaginary. So we can just hard code that in. Okay. What's the numerator? What's the denominator? You can work that out. Okay, you should know that. And where is this going to get stored? We're going to use these. So we need to pass their memory address here. Okay, so we use the ampersand symbol and we put these here. You can work that out. Okay, now once we've got that, okay, we should have the answer of the division. Okay, so just the division part. Okay, so just the ones with the arrows at it. As I said, this is one solution. Okay, one possible implementation. There are many ways to solve this. Okay, also, don't be afraid of extra code. If it's traceable and you can follow it and you can debug it, that and it's safer, always go with the safer approach. It's always better to have safe code than short code. And short code does not mean that it is faster as well. Okay, so be really careful about that. A code that might be 50 lines of code versus one that might be 3,000, the 3,000 may actually execute faster depending on the optimization that's done. Sorry about that. You can probably hear me drinking. All right. So now I've lost where I'm at. All right. So we've got the result of our division because remember we passed the addresses in here. And so now we're just going to add that to our sum. Okay, so we're doing the middle part. We're just going to use complex addition. We're going to do pretty much the exact same thing as we did here. Okay, so we're just going to use our sum real, sum imaginary, and at the end, we're going to pass the addresses of the sum. So address sum real and address sum imaginary. And in the middle part, we're going to put our division. Okay, so we can put our temp div division, div real, sorry, and our temp div imaginary. Okay. Okay. So once we've done all that, okay, so we've done the division, then we've added it. Done the division, then we've added it. Done the division, then we've added it. We'll notice with this formula, okay, so we've done this part here, okay, so we've summed them all up. But there's one more step, and this is this -1 here, which is the exact same thing as saying 1 over all of this stuff. Okay, so this sum of zk. So it means that all of this that we've got here also needs to be divided by 1. I mean, 1 divided by all this stuff, or the inverse of all this stuff. Okay. So to do that, once again, we use our complex division. So this isn't happening inside the for loop because this happens after we've calculated it all. So we can use our complex division. Once again, we're going 1 over. Then we want this over the total sum. Okay. So we're going to put the sum there. And where we want to store the result, you could put it into the total impedance, or you could put it into the total real and total imaginary. Okay. So remember here that you're passing an address in. Okay. And you can do what we did here if you like. And we can just put the address of the sum here, if you like, and then do the exact same thing we did here. Okay. So once we've done that, so total real should equal the sum real, and the total imaginary should equal, well, should become the sum imaginary. All right. So that gives us that. And once we've got that, we just need to go all the way back and put this into our memory. We need to put that here and here. We've got IR, we've got II. Okay, so impedance real, impedance imaginary. We've got our N. So we basically just need to go IR, N, stores, trade real. And II, N, stores, trade imaginary. And that's that function done. Now, as I said, there's lots of different ways to go about that second part, and that's why it's in blue. There's more efficient, and there's also better ways to do this, but I've done it this way, and you do it a different way that works and is safe, then that's fine. All right. So we've gone through two functions. Now we've just got the last function, which is probably the easiest function. So once you've done that, we then need to print all this out. And then we'll talk about the constraints. We won't talk about the bonus. All right. So the next part is the print results. And this basically takes the whole table of impedance, current, and voltage and puts it all into a table. Now, you'll notice that it gives you pretty much the format that it must be in. This first line here, I'm not going to explain because I think you can work that out. But what's important here is the order. So maybe I'll grab this and I'll put this somewhere else because we're running out of space. Oh, we're running out of a lot of space. Let me bring this. Results of complex division will be in an array to proceed further. I don't get what you're trying to say. Complex division, the result can be in a single. It's always in a single location. Well, two locations, one for the imaginary and one for the real. Doesn't matter if it's in an array. It doesn't matter if it's in just a single variable like we did here. Actually, none of these are an array. That's not in an array. That's in a single variable. That's a single variable. That's a single variable. That's a single variable. So none of these store the results in an array. So not sure what you're talking about. All right. So all right. So what we're going to do is we're going to draw up our table. Actually, we don't really need to draw up the table because the value is already here. So basically, we call this function. We should have access to a whole bunch of pointers. that should be connected to the imaginary parts for both, sorry, the imaginary and real parts for all impedance, capacitance, not capacitance, impedance, current, and voltage. Sorry. And these should be for each of the components that we have and also the total. So the very first line is the first thing that's printed. Okay. This is important that you understand what happens one after the other. So we first print this line. This line is not like the other lines. Okay. So it means that we are going to have one for loop to start with. However, we need to have a look what's actually going in a loop and what's not going in a loop. So if we have a look at this first line, this part here changes depending on how many components there are. Okay, so if there's 4 components, this would be another block here. If it was 5, there'd be another block. If there's 2, this would be shorter. So it means this green part is going to be a for loop. The total always exists. Okay, so that doesn't need to be in a loop. And same with this word components. This doesn't need to be in a loop. So I might use this color coding. Okay. So we're going to print the word components. We're going to have a loop, okay, that goes through and prints the letters R, C, or I. Now, note the spacing. It'll take you a little bit of time. Just try and work it out using the letters below. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 spaces before the C, etc. You get the point. Okay, so you should be able to work it out from that. All right, so for this for loop to get the R, C, and I, okay, we use, I should grab that. We use, where is it? We're going to use the components array, okay, because that tells us which component, okay? So I'm just gonna, I've lost everything. Good deal. Oh, there we go. All right, I'm just going to grab the function header. That's our function header, so I don't have to go all over the place. All right, so we're going to be using this components, okay, in this for loop to work out whether to print an R, C, or I. Okay, so it's going to be an if, and we can use our array notation to work that out. And then we can just print out the word total, okay, in a printf. Okay, so we've got components, we've got our for loop, which will print R, C, I, and then our total. Okay, this is just the words from now on. So we've done that first line. Okay, so we've printed out R, C, I, and total. We then get to the next line. Okay, you'll notice again that this part here at the start is a constant. So maybe it's on a different layer. So what I'll do, I'll get rid of that. Okay, so we're on the second line now. Okay, and I'll do some different colors for this. So now, because we're on the second line, I'll grab the layer. Alright, because we're on the second line, this part here, this Z brackets ohms, is just by itself, it's not in a loop. And same with this total part, it's not in a loop either. Okay, and then we've got all this middle section, which will depend upon how many components there are, which we can use n to find. So I should use the right colors. So the first thing that gets printed is this Z ohms, and printf. We then have our loop, so we're going to have a for loop, okay? And inside this for loop, we're just looking at our impedance real and our impedance imaginary, okay? And we're only going up to n, okay? Because we only want to get to this part here. You could go n+1 and it would include that part, but I'm not going to do that in this example, okay? Just for clarity. Okay, so we're just going to go up to n, okay? So from 0 to n, and print out each one of these, okay? So we're going to have a printf with 2% somethings, okay? Percent something, percent something. Don't forget that you can add the flags for your format specifiers. Okay, so inside of here, we're going to have a printf with 2 format specifiers, okay, and then the real part and the imaginary part for your impedance. Okay. Then once we've done that for loop, we're going to go down a little bit further and do the total. So we can just do a printf, exactly the same as that, but we just use n because we know that that's where the total is. Okay, going back right to the start of this problem. All right, so we've got that, and then v is going to be exactly the same as this, but just changing the variables. And then you should be able to print out the whole thing. So that's that. And then we'll talk about where is it? I've lost the constraints. There it is. Right. So I've been talking for a while. I'm just gonna have a quick break because talking for this long is kind of hard. So I'm just gonna have a quick 2-minute. Let's make it 3-minute break. Okay. Um, Alright. I'm back. Can you still hear me? Just say hi if you're still here. No people are still here. Hmm. Cool. Alright. So now just going to look at the constraints. So we're being a little bit harsher for this one. Okay, we've given warnings if you did do this in the first assignment. So if you didn't do it in the first assignment, probably shouldn't be a problem. Pi needs to be to 11 decimal places. This just helps us test that these are all the same, and it's not something external. You can only use these two libraries, the standard lib and standard IO. You cannot use the math library. You cannot use any other libraries. Okay? You can't use your own libraries either. All right? So you will get a 0 if you do significantly use any other library. You can't use any goto statements. Okay? Goto is only needed in very unique cases, and it's definitely not needed for this. Formatting needs to be specified. Okay, so try and keep the formatting the same. As I said before, you can count out. Yep. Yeah, it's a good idea to define pi. You can either use a macro or you can create a constant. It's fine. Either way you do it is fine. Um, and if you don't, it's fine as well. We're not too strict about that for this. Formatting needs to be exactly as specified, so try and make sure that the formatting is the same. If you do the bonus, the formatting will be slightly different, okay? And if you do the bonus, we're going to be even stricter on the formatting. Text to the user needs to be easily understandable. You can change some of the text to the user. One of them you have to do yourself. Make sure it is appropriate. Okay, so where is it? Here. There's no example given. A single line for invalid message to the user with a new line. The message is up to you, but it must be appropriate. Okay, so this is about you being able to communicate to the user clearly, and I've lost the constraints. Okay, so make sure that it's easily understandable. Okay, that includes a little bit of grammar and spelling. The program must print. Okay, do not put your student number in the comments. That's not good enough. It needs to print it to the screen, and it has to be your student number. Okay, and it needs to be your name and your assignment number. Okay, and you will get a 0 if not in this assignment. Okay, we need this on the assignment. Okay, and this is you saying that this is your work. Okay, it needs to be a C file. Do not submit an executable. Do not submit a text file. If you submit a text file, we cannot trust it, and we will not open it. Okay, and you will get a 0. Now, the code shouldn't crash due to a Stack Overflow or a segmentation fault. With this, as I've said in the labs, this includes if it has any chance that it could. Okay, so keep that in mind that it may look like your program's working, but if it's not written properly, there may be a chance that it could, and you will lose marks there. Okay, because we want code that will never crash, except for extraordinary circumstances. Okay, so it shouldn't crash because of your poorly written code. Okay, so I highly recommend you draw blocks and pointer diagrams and trace your program, and also double check everything as you're going and draw those diagrams. They will help you a lot to make sure that you're not doing the wrong thing. Types should be used appropriately. We pretty much tell you which types to use in this assignment, so you shouldn't have any problem with that. Comments, refer to the documentation guide, and make sure that you explain the functions and the solution. Okay, so that means function prototypes and a description at the top that explains the solution. These are important. These replace what used to be a report, and so they need to be slightly significant. Okay. There is a bonus worth 3%. It's a very small bonus. It's not too difficult. Yeah, that would cause an error. We'll come back to that. All right. The code should be around 100 to 250. If you go to 300 or so, it's fine. Okay. But if you go 700 or something like that, it's ridiculous. And you need to solve it using C, not another language. Okay. All the examples are on LMS. I've done it both in a video and in a picture. Just with the picture, you might have to scroll. LMS is kind of stupid. All right. Now we're going to have a look at this. Okay. So a call to calculate impedance. Actually, we'll do this slightly different. We'll do it here. All right. So calculating impedance expects a pointer to the start of the impedance real array. So basically, we pass this pointer. Okay, so we pass IR. Now, IR is a double star, so that's perfectly fine. I don't need to add a star in front of it or anything like that. Same with the next one. Components, as we said, when we see int components with a square brace after it, basically that's the same as saying int star components. So if we need to pass our components in, then we should pass C in. We can't pass star C in because then we're passing a single int. We can't pass C square brackets because we can't declare C as we implement it. Okay, so there shouldn't be any square brackets. And we don't pass the address in because it's not an int star star, it's an int star. So it's just C. Okay? Keep in mind that these are the same thing. When you see the square brackets, it's the exact same thing as int star. Okay? This is not a variable. Okay? You will only see this in declaration. Okay? You should never ever use this unless you're declaring something. And in here, we are declaring something. So we should just pass in components. Here, we're just passing in values. Here, we're just passing in n. Here, we're just passing in frequency. And here, we're just passing in choice. That answer the question? Okay. Don't look at these and just try and pass the exact same thing in. Okay, a lot of people try and do that. Is it good that I create two pointers which point to the same position while taking inputs for value? Yeah, so while taking inputs for value, as I said, you can use pointer arithmetic if you prefer, or you can use just array notation. It's up to you how you want to do it, but if you want, we can go through this. So we did the array notation version before, but if you are going to use pointer arithmetic, make sure you create a pointer, okay, that will point at the start of your array. Okay, so it's V, all right. And then when you use your scanf, okay, you are now passing in that memory address. Um, you're passing in that memory address, and then you're just incrementing. So either one is fine. Okay, you can use a pointer. Um, that should be outside of your for loop. Okay. So you can use pointer arithmetic. You just need to remember to first set it to the right location and then pass it. So referring to the question before, with the brackets, so the person asked about the complex division in the brackets. You'll notice that these brackets have an index in them. And so I'm referring to a value. And this is the one that I was referring to. Okay. So if I have a function, okay, func, let's say int a, okay, then, and I have an array, let's say b, okay, because this is an int, okay, when I call this function, I need the square brackets, okay, to pass the number 2, okay, because adding the square brackets changes b from an int star to an int, okay, and we're getting a value. However, if this was an int star, then I should only pass the b, or if this was int a, this is the exact same thing as an int star, and so I should only pass the b. Okay. Remember that b is a pointer to the start of the array. Okay, so it depends on the situation if you include a reference to the particular index or not. Okay, does that make sense? So it depends what it says here to whether if you include square braces or not. But in any function call, if you do use square braces, they have to have something inside them in the function call itself. Okay, so func and func2, let's say, it's an int. Let's do func3. So this is int star a, and this is int a. So func, that would be legal. Func2, that would be legal. And func3, let's say 0, that would be legal. Okay. I haven't drawn what the functions are, but you get the point. These are function prototypes. Okay. Okay, because this one's passing an actual int, so that's an int in there, where this one's passing the pointer to the start of the array. Okay, and this here is int star, this here is int star, the pointer to the start of the array is int star. Ooh, any more questions? That's all right. Yeah, if there's any other questions, I'm happy to answer them. If there's something you want to go through, as I said, I'm not going through the part that says you need to work it out for yourself. Um, okay, so that's for you to show us you can solve a problem. I have one word. Ah, okay, cool. With these assignments, try and go back and try and um, make sure that you can try and solve it when you get to the exam. Um, these instructions here, whilst they are trying to be clear, they're trying to make sure that you can turn it into code. But in the real world, you won't get any of this. You'll just get the problem. So when it comes to the exam, when it comes to understanding, um, here you're basically just turning what it says into code. Um, and for the exam, you'll do something similar. But if you really want to master this, you should be able to take the question and then put it in. Now, we've put some limitations on that because we've told you to do it in a certain way. But if you've deviated from the way while staying within the constraints, that's excellent to see. Okay, and this is why I mentioned that and why I've only given you one solution that has some parts that aren't really necessary in here to see if you do it a different way. Okay, so because even if you get 100%, we do want to see who's gone and done further. Now, a hint for the bonus. Let me get the bonus up. What is it? Um, a lot of yeah. So when choosing the component type, it is being stored in an array. So where are we? If we go down, we've got um, the components array, which is here, which we created a number for. Okay, this is dynamically allocated, so this is what we did here with the malloc. Okay, and that one is here in our diagram. Okay, we can't store it in separate variables because we don't know how many variables we'll need when the program starts. Because if the user says, "Oh, I want 50,000 components," and then the next user comes along and says, "I want 2 components," we won't know how many variables to contain. So we do need it in an array, and that's step 4 that we create that array. Okay, and that's our C array or components array that we created earlier at the start of the session. Oh yeah, I was going to get the bonus. Does that answer the question? Yep, cool. All right. Bonus, 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 bonus. There's a bonus. Oh, there it is. Oh, yep. So I'll give you a hint about the printing as well. Um, so I'll copy the bonus in to this almost full document. Also, before I do that, I'll mention something else about the printing, which is kind of important. Lab reference. All right. So with your printing, and we did this in the lab with the complex numbers, we used this flag here, this plus flag. So we wrote something like percent plus D or percent plus F, etc. And this just means that it always shows a sign. And so, for example, if I did printf there, and I wrote percent plus D, and I put, now I'm just going to put a constant here, 21 here. Okay, so I've got the literal 21. When it prints to the screen, it'll print plus 21. And if I did printf, and if I change that to minus 21, it would print minus 21. So it just means that there's always a sign at the start. Okay, and that you'll need for this assignment. Okay, so just keep that in mind. However, with the bonus, you've got the sign outside, okay, of the brackets. Okay, now with this, okay, it shouldn't take extra lines of code. You might find the ternary operator helpful when doing this. You can do it in a bunch of different lines of code if you prefer, but it should, the optimal solution should be the same lines of code, okay? But it requires some tricks with your formatting and also, actually, I won't give any more hints than that, okay? A little bit of math might help as well. Okay. So for the normal solution, the pluses are inside the brackets and the minuses, but for this solution, for the bonus solution, it's outside. This one's a bit harder than the first assignment's bonus, okay? But some people might get it. What else is there? But yeah, for any solution, this plus, you need it. What else have we got? And in terms of your next assignment, I've just finished writing the code for it, so it should be out hopefully soon. I've got to write the document, but we'll get there. It's a bit different than this one, but it has a lot of the same components. It'll have the dynamic memory once again. But it will be two-dimensional. And user's choice. As a unsigned car, I'm pretty sure I said, yeah, so you can store it originally, but because you can't change the types here, it will be implicitly cast. So whilst I understand what you're doing, you're trying to use a smaller type. I'm going to enforce this. So it's fine as an int type anyway. Because basically it's the same as the bus size on the computer. So it really won't make much of a difference. So an int type's going to be just as efficient. You are considering space, which is good, but in terms of speed, it's going to be the same speed. But if you want to store it as a car and then change it, that's fine. But the type when you pass it needs to be the same. Um, how long have we been going? So how long do you think until this upload? So usually YouTube takes a little bit of time to process it. You should be able to see the last 2 hours though, always. I'm pretty sure. I don't know, YouTube's weird. Um, it depends. Um, hopefully quickly. Hopefully by tomorrow. But I've had some videos that upload very quickly and some that are a bit slow. So I can't guarantee that, and I haven't kept a local copy, unfortunately. Probably. Um, probably. I hope. Um, usually it's within 24 hours. Um, but I have had it where it's longer before, where it's been about 2 days, just because I don't know. I really don't know the reason. It's a day. Um, Any other questions? It doesn't have to be about the assignment as well. If there's any other questions, feel free to ask. Um, so the way that I would solve this problem is okay. So I wouldn't worry about maximizing marks. The way that I would go about this is basically I would do the printing, the getting the values. Ooh, that's a great question. Ah, okay. I'll come back to that in a second. All right. So where are we? All right. So what was I saying? So I would do that one. I'd do that one. I'd do that one. Do that one and that one. Okay. I do all 5 of those, and then I do 11. Okay. The reason I would do those first is because I want to firstly this is trivial, so I don't you might want to just check that it did get the right values. But what I want to check is if I create this dynamic memory in 3, 4, and 5, does it free okay? Because if it doesn't free okay, then I've done something wrong with my dynamic memory. Um, I might still have done something wrong, but I've done something significantly wrong if I can't free that memory. So that'd be the first thing I'd do. Then I'd do 6 because I can't do much else without 6. So I'd get 1, 2, 3, 4, 5, 11 working first. Then once I've done that, I'd do 6 and get that working. I would then check that that works. So I'd just put a for loop and check that these exist inside my array. there's no point doing the calculate impedance if this doesn't work because it's dependent upon these values here. Then what I would do is I wouldn't do any more here. I'd go to my calculate impedance function and I would do, where is the calculate impedance? Yeah, so if you get a big error, a runtime error that comes up, then you know that it can't be freed. Okay, it's you've done something wrong. So you will get a runtime error, and it's a big one. Okay, so it'll give you the whole stack, and it will give you a bunch of data, and the errors message will change each time, but you'll know it when you see it. I might make an example of it if I get a chance. So once I've done that, I would do the calculate impedance. Okay, just this part though. Okay, I wouldn't do the second part. So once I've got that working, okay, so this might be a little bit hard to follow, but I've just done 6, and then I do the calculate impedance, but I just do this part here. Okay, so I just do the individuals. I'm not going to worry about the total yet. Okay, then I would call it. Okay, and make sure that the memory is being freed still fine. Okay, I might also print out the values and check that works. The next thing that I would do is I would do the print function. Okay, so wherever that was, I would do the whole print function. Okay, and the reason I'm doing my print function is there's no point calculating current, voltage, the total impedance, etc., without being able to see if it's working or not. And so I do the print function. I can test if the print function's working correctly because I've got some values already just from these ones that are highlighted in green, actually. So these ones here. So I do the full print function. Once I've got the print function working, I would do step 10. Okay. Now, obviously, the totals aren't going to be there. The currents aren't going to be there. I'm going to get garbage values for these, but I can see if the impedance is working. Once I've done that, I would go and finish off your impedance function and do this part. Once I've done that, I can just run the program again. And because I've done the print, I can check it every time I make a change to it. And then I just go off and finish off the last 2 bits. Okay. So I finish off those 2. And that's basically, I think, one of the most suitable ways to solve this problem whilst testing it at the same time. Because if you just go through this whole thing, you can't really test the output. If you rush and do this, then you won't be able to see if it works or not. So it's a bit about finding dependence between your functions and also your testing. And your print function saves you a huge amount of time because it's giving you the test answers. And you can go, oh, it's working, or oh, why is only this one not working? Now, so someone asked a really good question, and this is the gets function. So I'll get the I'll get the the C definition up for it. All right, so where are we? All right, so someone asked about a function called gets. Okay, and this function, if you try and use it, it will give you a warning. And this warning basically says this function is dangerous, do not use it. And it is dangerous. It caused one of the early major viruses, um, and it's been used for getting through security on computers. It's a really nasty function. Um, Basically, this gets function, what it does, okay, so it reads um, your input, okay, kind of like get car, um, and it stores it into a pointer, okay. So where are we? Where are we? So it has the format like this. Okay, so that's its prototype. Okay, that's its declaration. And what's dangerous about this? Okay, so we have to go into memory. Okay, this is not stuff that's on the exam. It's just someone asked, and it's really interesting. Um, so you'll see that we're passing in a pointer to a string. So let's say I create a string pointer, or even better, let's say I create uh, car string 4. Okay, so I've got 4 cars in memory. Okay, and I've got this string pointer that points to these. Okay, so this is it's a bit hard to explain, but oh, sorry, we're not using dynamic memory anymore. All right, so this is a bit hard to explain using box and pointer diagrams, but I'm going to kind of go between both so that you can understand as best as you can. So we've got this array called str, and it's of type car. Now, it's a string, so the last character should be the null terminator. And in memory, it should be the null terminator. Okay? What this gets allows us to do, okay, we pass a pointer in, okay, and that's this pointer. Now, that pointer is stored in memory as well, okay, so that pointer's pointing to here, right? Now, when we pass this pointer in, we can start injecting malicious code into our code, okay? And the way this is done is if you know where stuff is in memory, okay? So for example, super important stuff here, okay? What we can do is we can on the console enter something that's say 20 characters long. And what gets will do is it will go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And it'll overwrite that data with whatever you've put on the console. And that could be something quite dangerous. And you can intentionally inject code into whatever's running. And you could intentionally inject values into variables that the user would normally not have access to. And this is why gets is a dangerous function. Does that make sense? Um, I did do a longer version of this in one of the streams last year. Um, if you want me to go through it in detail, I can refer you to that. Um, Basically, the problem with gets is that it doesn't. It just if you enter 20 characters and your array's only 4, it will just keep writing into memory. Okay, so just don't use it. I can't remember what the I remember. I don't know where it is. Anyways, um, no, I'm not going to explain function pointers. Um, that's going to take way too long. And I prefer you be comfortable with pointers first because it's quite complex. Here we go. All right, is there any other questions? Or is that good? I think everyone's starting to leave. So I think this is other questions so that it gets uploaded in time. Um, I might drop it there. If you're writing a question, just say so, and I'll stay on. Otherwise, all good. Thank you very much. Hopefully that was helpful, and good luck with your assignment. And yeah, this you should be able to do well. Okay. Make sure you're testing as you go. That's the main thing. Cool, cool, cool. All right. See you later.